Welcome to iTTV for Form 4 Physics. The title of this lesson, Scalar and Vector Quantities. When we talk about motion of an object, we talk about words such like distance, displacement, speed, velocity. These mathematical quantities can be broken into two main groups, vector and scalar. A vector quantity is a quantity that has both direction and magnitude. A scalar quantity is different. It only has magnitude. It has no direction. By the end of this lesson, what I will hope is that you understand what scalar and vector mean, be able to give me examples of a scalar quantity and a vector quantity, and be able to do basic calculations and find displacement or distance, speed or velocity of a given object in motion. In the slide, you see the traffic control tower at Kuala Lumpur International Airport. The air traffic control tower needs to know the position, height, speed and direction of motion of an aircraft in order to monitor its flight path. The position and height of an aeroplane gives its displacement, which is its distance and direction from the air traffic controlling tower. The speed and direction of motion of the aeroplane is defined as its velocity. Scalar quantities. A scalar quantity is defined as a quantity that has magnitude only. Typical examples of scalar quantities are time, speed, temperature, and volume. So a scalar quantity, like we've said, is defined as a quantity that has a magnitude but no direction. If you think about temperature, we have a magnitude value for temperature, 30 degrees Celsius, 50 degrees Celsius, but there is no direction. It's not 30 degrees Celsius to the left or 50 degrees Celsius to the south. We just say the temperature's value. So this is what we mean by magnitude only, but no direction. Other examples of scalar values are things like density or energy, which also have magnitude but no direction. Scalar quantities. A scalar quantity or parameter has no direction component, only magnitude. For example, the units of time, minutes, days, hours, etc. represent an amount of time only and tell nothing of direction. Vector quantities. A vector quantity is defined as a quantity that has both magnitude and direction. The magnitude is represented by the length of the vector. So here, a vector quantity is quite different from scalar. Here we have both magnitude and direction. Now we can represent a vector quantity by drawing a vector line. The line and its direction give us its direction. The length of the line will be giving us its magnitude. So we have both magnitude and direction. Examples of vector quantities are things like velocity, force, acceleration, all of which have a magnitude and are acting in a particular direction. An example of vector. Using north-south and east-west reference axes, vector A is orientated in the northeast quadrant with a direction of 45 degrees north of the east-west axis. Giving direction to scalar A makes it a vector. The length of A is representative of its magnitude or displacement. So if you look at that slide, you can clearly see that the line A has got, firstly, a direction. The direction is northeast at 45 degrees north of the east-west axis. Secondly, the length of the vector will give us its magnitude. Here what we need is a scale. Let's say if a scale says 1 centimeter equals 10 newtons and the line is 5 centimeters long, that means the magnitude would be 5 centimeters times 10, which would be 50 newtons. So we have both a magnitude and we have a direction. Example, we have a car going around at a roundabout at a cross section of a road. The car is moving at a constant speed of 50 kilometers per hour. Will the velocity of the car change? In this case, the magnitude of the speed of the car does not change. The speed remains constant. The direction of movement changes as the car keeps moving around. Thus, velocity of the car changes because the changes in direction even though the magnitude is constant. So what are we trying to teach you in this slide? Well, two things. One, the difference between a scalar quantity and a vector quantity. Speed is a scalar quantity. It only has a magnitude, but it has no direction. So even though the car keeps changing its direction, its speed does not change. Its speed is 50 kilometers per hour all the time. But if we look at velocity, velocity is speed with a direction. Now, because the direction of the car is constantly changing, this means that its velocity will be constantly changing. So understand the difference between scalar and vector with regards to speed and velocity. The speed does not require a direction, so it does not change. The velocity requires a direction component, so it is constantly changing. Addition of vectors. There are many situations where addition of vectors are involved in solving daily problems. Many of the problems are usually involving force. To add two vectors, we draw these vectors to scale as arrows pointing in the appropriate direction, then place them head to tail. For instance, in the diagram, there is a block of wood placed on top of a table. If the wood is pulled with a force of 5 newtons to the right, we may use an arrow 5 centimeters long to represent the force 5 newtons. So what we're doing is drawing an arrow that will represent to us the force. The direction of the force and the magnitude of the force will be represented in this vector. So let's sketch this on the board so that we can understand it slightly better. So what we said is we have a block of wood placed on the table. So here I have a block of wood. I've said that the block of wood is being pulled to the right-hand side by a force of 5 newtons. Now, if we say that 1 centimeter represents 1 newton, then 5 newtons would be a 5 centimeter long line. And the direction is to the right. So I can draw the force acting up here, like so. Now this is not to scale, but we will put in the values nonetheless so that you understand what we're doing. If this is 5 newtons and I say 1 centimeter equals 1 newton, that means this line needs to be 5 centimeters long because the force is 5 newtons and it is pointing to the right-hand side. So this line, this vector, is representative of our force. It gives us a magnitude and a direction. Addition of vectors. Another force is now pushing from the other side of the block as shown. The resultant force, the addition of the two vectors, can be represented by a line of 8 centimeters towards the right as shown. So if you have two forces acting on an object, we are adding another force here. Let me draw it in. We have another force coming in on this side, and this force is 3 newtons. So this line over here should be 3 centimeters in length. to represent 3 newtons. Now, the total force acting on this block will be the front line and the back line added together. So the 5 centimeters and the 8 centimeters. So the resultant force, let's write that down here. The resultant force can be represented by a line eight centimeters long going to the right. So we have both, once again, a magnitude and a direction. The magnitude is 8 newtons, represented by the 8 centimeters up here, and the direction represented by the to the right statement under the arrow. So this is how we can do vectors. We can also do subtraction of vectors. Subtraction of vectors. In this case, the net force is 5 minus 3 equals 2 newtons towards the right direction. So in this case, what has happened is this force is going in the opposite direction. Because it is going in the opposite direction, my resultant force is 5 plus, if you're going in the opposite direction, we give it a negative value, 5 plus negative 3, which gives me 2. So what I get is a resultant force of 2 newtons, but this time going to the right. So how would I represent that? I would use a smaller, that's right, vector, which is only 2 centimeters long, going to the right-hand side, like so. So understand either addition or subtraction of vectors. We draw the lines, the line, that vector, gives us both the magnitude and direction. Don't forget, a correct scale is very important in order to do these diagrams. Principle of parallelogram of vectors. A cargo ship is pulled by 2 tugboats at an angle of 45 degrees as shown. The force pulled by the tugboats are 5,000 newtons and 8,000 newtons acting at a point O. We can find the resultant force by the 2 tugboats using the principle of parallelogram of vectors. So when you have 2 forces but they are acting at an angle to each other, we can use a parallelogram to work out the resultant vector. On your slide, you can see the parallelogram that we are drawing. Firstly, we draw 2 lines from 0 to represent the vectors, the pull of the tugboats. The direction and magnitude must be accurate, and the length of each line must be in proportion to the magnitude of each vector. We can use 1 centimeter equals 1,000 newtons. So let's go up to the board and draw this diagram for ourselves so that we understand how we do it. At home, you should be getting a protractor out because that's what we're going to require. So let's begin by drawing the object. The object in this case is a ship, like so. The ship has 2 forces pulling on it. The angle between the 2 forces is 45 degrees. So what we need to do is draw a line going like so, and a second line going like so. This angle is 45 degrees. Now, the bottom vector represents a force of 5,000 newtons. If we use a scale, 1 cm equals 1,000 newtons. If this line is 5 cm long, it will be 5,000 newtons long. The second line up here, which represents the 8,000, needs to be a bit longer because it's 8 cm long. So let's extend this line to about here. And let's put in the value, 8 cm long. So we've got our main components. Now what we need to do is complete the parallelogram. So we complete the parallelogram by drawing another 8 centimeter line here. Make sure that this line and this line are parallel to each other. Then complete the diagram by drawing a line over here so that this line and this line are parallel to each other. Now that the parallelogram has been completed, what we do is we connect point O, which is over here, to point R over here. Like so. We need to measure this because we don't know how many centimeter this line is. Once you've measured that, all you do is you multiply by 1,000. So R equals X times 1,000, which will give you your resultant force, and we can easily work out the direction from the diagram. So we have our vector quantity. Our resultant force has been worked out. We know its magnitude and we know its direction. So let's try a question. A boy walks 40 meters due east from a point P and then another 30 meters due north. A. What is the total distance traveled? B. What is the boy's resultant displacement from P? So we have two parts that we need to work out here. His distance traveled and its displacement. Firstly, we need to know which one is which in terms of scalar and vector. Remember, distance is scalar. We don't care about the direction, we only care about the magnitude. Displacement, however, is a vector quantity. We need to know the direction that the person is traveling and the distance in terms of displacement. So let's go up to the board and sketch what has occurred. Now, as the question says, a boy starts traveling. Let's say he starts at this point here, point P. Now, what we've said is the boy travels 40 meters from this point to the east. So he travels this way. Let's use a representative of centimeters for the 40 meters. Let's say 1 cm is 10 meters. So if 1 cm is 10 meters, then this will be 4 centimeters long. Then he moves north 30 meters. So he goes upwards. Let's use a different color for the upward motion. This way. So this is 3 centimeters. Now, the total distance traveled by the boy is the entire length that he has moved from start to finish. The length that he has moved is 4 centimeters plus 3 centimeters, which is 7 centimeters. So our distance equals 7 times 10, which equals 70 meters. Now, your displacement is your change from your point of origin. You started in a place and now you've ended up in another place. What is the actual distance that you've moved from your origin to your new point? Now, if the boy started at P, he has finished up here. So his displacement will be this distance. This is what we want to find for his displacement. And we can find this by using Pythagoras theorem. So to find the distance, that the displacement of the boy, displacement, like I said, we use Pythagoras theorem, which will be 3 squared plus 4 squared equals x squared. And what we're looking for is x squared. So if we do the maths, 3 squared, very good, 9, plus 4 squared. Very good. 16, add the two numbers up and do a square root. So the square root of 25 gives us a value of 5 centimeters. So his displacement is 5 centimeters. So we know that the value up here is 5. And we can change it back into meters by multiplying by 10. So his displacement is 50. This is how we can calculate his displacement. But in order to work out his actual displacement, we also need to find his angle. Meaning we need to find this angle over here. And we can find this angle by using tangent. Tan equals opposite over adjacent. In this case, 3/4. And you should be able to calculate this and get a value of approximately about 51 degrees. So, distance 70 meters. Displacement 50 meters at an angle of 51 degrees to the northeast. And this is how you can understand, hopefully, the difference between scalar, which has got magnitude but no direction, and vector, which has both magnitude and direction. Summary. Physical quantities can be divided into scalar and vector quantities. Scalar quantity has magnitude only. Vector quantities have both magnitude and direction. You must be able to know the examples of each. Remember, scalar quantities are things like speed, distance, mass, temperature, energy. Vector quantities must have a direction to them. These are things like velocity, acceleration, force. So remember the differences between the two of them. Finally, the resultant vectors can be calculated using graphical method. Remember, we can work out the vectors by addition, subtraction, parallelograms, and also simple Pythagoras theorem when someone moves from one place to another place. This is all the time we have for this lesson on scalar and vector. Thank you for watching iTTV.